I know I promised imaginary numbers, so the title of the section is kind of misleading. It's called the complex numbers. And don't get scared or nervous about complex numbers. They're not complex as in they're really tough and this is going to be a really hard section and you're going to hate it and this kind of thing. It's just called complex because these numbers are made up of imaginary and real put together. They're not really that complicated, as you'll see. So it's kind of a misleading name. It's just, again, complex because it's made up of two parts. So they're not simple, they're complex, I guess. But anyway, let's talk about imaginary numbers. We've talked about them before. We said, in basically the first section of this whole chapter, we said when you end up with a negative inside of a even indexed root, it's going to be an imaginary number. But the number I, we say, I guess you can kind of imagine I stands for imaginary. It's the unique number for which it's the square root of -1. And you notice that if I is the square root of -1, what would I squared be? Imagine. Okay, well, if I is the square root of -1, then I squared should be that thing squared, Because I guess imagine, here's I. By definition, I is the square root of -1. That's the definition of I. If you want to know what I squared is, just square both sides. And the square root and the square will cancel just to leave the -1. So it's not really a mystery, or it's not like someone made this part up where I squared is -1. It's that if you make this definition here, I is the square root of -1, consequently it comes out that I squared is -1. And that seems like something kind of random to point out right now. Like, who cares? If I know what I is, why do I care what I squared is? It'll actually help us in the later examples of this section to keep in mind that not only is I the square root of -1, I squared is -1. So notice that there are actually a lot of imaginary numbers out there, because as we talked about in the first section of this chapter, anything where you have a negative inside a square root, or a fourth root, or a sixth root, an even root, anytime you have a negative inside, doesn't matter what the number is, -1, -2, -3, on and on, it's going to be imaginary. So notice it's the square root of -1, so that's only one imaginary number. There's all kinds of imaginary numbers aside from I. But in example 1, we'll see here that you can get any imaginary number in terms of I. As in, you can make it look more like a real number times I. So let's see, there's not really any directions behind it. We'll just kind of jump into it. Let's see, for example 1, part A here, we have the square root of -5. So I guess what we want to do is, we kind of want to extract I, which is the square root of -1, out of this thing. So I see it's a -5 in there, but what if I rewrite it inside as, I want to take the -1 out, so I'm going to write it as 5 times -1, That kind of thing, because I'm kind of trying to separate the imaginary part, the -1 inside a square root, from the rest of it. And of course we've seen before that you can always split up, when you have multiplication inside a root, you can split it into two roots. Here, so I'm going to give 5 his own square root, and then the -1 his own square root. And that way I know what this guy's called. That's what we defined I to be, right? So I can replace the square root of -1 with I. And there it is. So now we've rewritten it as a real number, because now square root of 5 is no longer imaginary, it's real. There's no negative inside the square root. It's a real number multiplied by I. And that's really what they mean by express it in terms of I. So that's just so you know, you don't have to do that long process every time, extracting the -1 out and then splitting it up. If you want to just kind of observe what happened from the original problem to our answer, you can kind of think of it as, well, what happened? The negative disappeared and an I popped up instead, right? So if you want, you can kind of just memorize it like that. You can just get rid of the negative and place I to the right of the root. Of course I doesn't want to go inside the root. It's going to be, because I itself is already a root. So you're just going to get rid of the negative that's inside the root you're given, and then put an I on the side instead. That's kind of the shortcut. Maybe we can do that with the next two examples here, just to make it faster. So here we have, in part B, the square root of -64. Like we said, you're going to get rid of the negative, so it's going to be now positive 64 inside the root. Just to compensate for that, we're just going to throw an I on the side. Not inside the root, but outside the root. That's why I kind of like to put this corner on the root so I know where it ends. And so I know the next thing, the thing to the right won't be inside the root. And this one I can actually go a little further because in the last one we had a square root of 5. There is no square root of 5. But 64 does have a square root. It's 8. This one simplifies down to a nice real number that's, just a whole number times I. So it's kind of nice. It does make it look a little nicer, huh? If you write it in terms of I. Okay, and this last one's similar, but remember that I, when you replace I, you're replacing this negative inside. So the negative outside is not going to go away. It'll stay. You're just getting rid of the negative inside. Now it's going to become positive 32, and then you're throwing an I off to the side there. That's about all we can do, although 32 inside a square root can be simplified. I'm going to rewrite 32 and prime factor it. 32 can be 2 times 16, or you could break it down 4 times 8, whatever you want to do. 16 is 2 times 8. 8 is 2 times 2. Oh, sorry, 2 times 4. And 4 is 2 times 2. There we go. Since this is a square root, we're looking for pairs of primes. Here's a pair of 2's. Here's another pair of 2's, but there's kind of one odd man out. So when I rewrite the square root of, or negative square root of 32, I'm going to have one pair of 2's, a second pair of 2's, and one last 2 that's kind of doing his own thing all by himself. And then I'll give each of those 2's their own square root. 2 squared gets his own square root. The other 2 squared gets his own square root. And that last square root of 2 gets his own. And of course these square roots cancel with the square. So it'll be a 2 times a 2 times the square root of 2. And the I is still hanging out there. The last step would be just multiply the 2's outside. 2 times 2 would be 4. There we go. Beautiful. So it looks complicated. I think what you want to see is the fact that it started out as imaginary. You want it to be the I on the side is the imaginary portion, and what's left in the front, or on the left side, is real. You want to make sure that, it looks like a real number times I. And that way, kind of, any imaginary number can be broken down into some kind of I type expression. Whew, all right. So that's kind of dealing with imaginary numbers. Now we kind of move on to what the title of the section's all about. What do they say here? This definition, a complex number. What is a complex number? It's any number of the form a plus bi, where a and b are real numbers. So here, just below, this example is not really asking you to do anything. It just wants to show you this is what those look like. Here's an example of a complex number, 5 plus 4i. So there, I guess your a, notice a is like they call that the real portion because it's not next to I, and b is the imaginary portion because it is next to I. So here it's like our 5 is the real part, and then the 4 must be the imaginary part. This isn't too important, it's just, I don't know. Especially if you're a STEM major, you might see this again, so it's good to have seen before. And the second example, this is also a real number. Even though there's a square root involved, this is still a real number. There's no negative inside that root. So the square root of 3, that'll be the real part. And then the coefficient of I is actually not just 2/5, but negative 2/5. That'll be the imaginary part, because that's the coefficient of I, the imaginary number. Alright, another kind of surprising example is this next guy, pi I. It seems too complicated, but still it's a complex number. It just kind of looks like a plus bi, but there's no a, right? It kind of looks like the a is 0, 0 plus pi I. So it's kind of missing its real part. There's nothing in the front adding with the I term. So it'll be more like 0 is the real part. There is no real portion. But pi must be the imaginary part. And remember, pi is just a real number. All it is 3.14, on and on and on. I mean, the decimal goes on forever, but it's still real. Because there's no negative inside a square root. That's the only thing that would make it not real, if it's imaginary. And this last example is the most surprising one, maybe. It's just -1. It seems like, wait, that's just a number that I know. You know, we've dealt with -1 all the time. But it's still complex because you can think of it as, that's the real part, because I don't see an I. And then the imaginary part is 0. Because 0 times anything is 0. So it's kind of like the real part is the number you're given. -1, and then the imaginary part is 0. You're missing your imaginary part. So it's really anything you can think of as a complex number. Like all the numbers we've dealt with so far, all fractions, all roots that are real, all whole numbers, all that kind of stuff, and decimals as well. They're complex numbers. They're just more like this last guy we saw, just that their imaginary part has been 0 the whole time. We just didn't know we were dealing with complex numbers. So anyway, what this section is mostly about is taking complex numbers and learning how to add them together, subtract them, multiply them, divide them. That's kind of the bulk of this section. And I want to point out, I guess I might as well point it out now, that what we want to do, like we said, we're going to be adding, let's see, add. We will learn to add, subtract, multiply, divide complex numbers. That's what this section's all about. But the main thing we want to keep in mind, and I'll keep reminding you of this throughout this section, is we want our answers to look like a plus bi, that complex number. So if we ever add, subtract, multiply, divide two complex numbers and our answer does not look like this, it doesn't look like something plus something I, then we'll have to do something to make it look that way. Because we kind of want everything to stay in the family of complex numbers. When you combine two complex numbers by adding, subtracting, multiplying, or dividing, you want to make sure that the result is going to be another complex number. So we'll have to keep that in mind. Everything we do here, we'll keep that in mind. Okay, so example 2 talks about adding or subtracting two complex numbers. So let's look at part A here. So even though there are parentheses, notice you have 3 minus 4i. You're kind of thinking of that as one complex number. That's like a plus bi. Even though there's no plus, still imagine it's a real part and an imaginary part. And here's a second complex number you're adding, and it kind of has that form, a plus bi. You want to add them together. So the parentheses, they're not really there for any reason, because there's nothing to distribute or anything like that. I think they're just kind of there to show you these are two different complex numbers we're trying to add. But if you want, you can just remove the parentheses altogether. And I was going to put a plus in the middle, but I noticed plus a -5 is really just -5. You don't really need to put the plus. And the best thing about this is exactly what you would think. Imagine this was like the i's were just x's. What if this was 3 minus 4x minus 5 plus 7x? You just combine like terms, right? It would be the 3 and the -5 make -2, the -4x and the 7x make 3x. And that's really it. So we're going to do the same thing, except keeping in mind I is like a variable kind of. But we have the real parts are 3 and -5. Those add up to -2. The imaginary parts, -4i and 7i, add up to 3i. And that's really it. And I should just check in the end, does that have that form, a plus bi? Yeah, it does. The real part is -2. Bi is 3i. Okay, yeah. I think it looks good. But if you had written your answer backwards, what if you put the 3i first and then the -2? Even though we're used to that as far as x's go, you want to put it in descending order of powers. When it comes to complex numbers, you don't want to write it in that form. You want the real part first, so the -2 comes first, and then the imaginary part, the 3i, should be second. Let's try part B. This one, though, is subtracting. Notice there's a minus in the middle. So there kind of is something I need to do before I remove parentheses. This minus is meant for everyone in the second parentheses, so I better distribute it. But the first parentheses I can just remove outright, because there's nothing really to do. But I better make sure I distribute this negative. It'll make the 1 negative and the 3i positive, because it was a negative. But once you do that, that's kind of the only thing that makes subtracting complicated. Now you can just kind of combine like terms. Here I have a -4 and a -1. Those are the real parts. That makes -5. And then the imaginary parts, I and 3i, add up to 4i. And I think that's it, because that does look like the form a plus bi. As long as the real part's on the left, the imaginary part's on the right, you must be doing something right. So there it is. It's not too bad, right? It seems scary, I think, because the I, but you don't even care what I is. Notice we're not even using the fact that I is the square root of -1. We're just kind of dealing with I as if it were a variable. So part C is similar. It's just, notice the first complex number has a real and imaginary part. but the second complex number only has its imaginary part. But it's not a big deal. I'm going to remove the parentheses on the left, because they're not really there for any reason. But the parentheses on the right, if I want to remove them, I'm going to take the negative negative and make it positive 7i. Alright, now I know my answer should have the real part first. There's only one real part to this, negative 2, so I'll bring it down. But these two are both imaginary. They can combine. Negative 5i and 7i makes 2i. There, that's it. And it does look like it's in the right form, a plus bi. Good. Alright, so adding and subtracting, you can see it's not too bad, right? Multiplying will be a little more complicated, and then dividing will be quite a bit more complicated, but we'll get the hang of it. So multiplying. Multiplying, it's not too complicated, it just seems like there's more steps. But let's see, you actually, imagine part A. What would you guess to do here? Especially, what if you were kind of thinking of this is your little thought bubble. You're thinking of this, what if the I was an x? It's negative 3x times 2 plus 7x. I would think to distribute, right? Negative 3x times that guy, negative 3x times that guy. That's exactly what you can do. This one you're going to just distribute that negative 3i in. So we have negative 3i times 2, that's negative 6i. And you have negative 3i times positive 7i. That'll be negative 21i squared, since it's a I times a I. Alright, and that's really, at this point I think, well, what else can I do? I can't really stop though, because this doesn't look like it's a plus bi, right? I see the I here. Okay, so that's probably the bi. But you're not supposed to have an I squared in your answer. It's supposed to have this form, a plus bi. No I squared in the answer. So this is where I say, oh, what do I do with that I squared? Well, remember in the very beginning of this section we said, we pointed out, right when we defined what I was, we pointed out that I squared is negative 1. So what we're just going to do is every time we see an I squared from now on, we're going to replace the I squared with negative 1. That'll be my next step. I'm going to take what I have found. It's negative 6i minus 21i squared. But where that I squared was, I'm going to replace it with negative 1. Here we go. Because like we said, yeah, in the very beginning, I squared is negative 1, so you can replace it, no problem. And let's see what happens. We'll simplify that. Negative 6i, then you have minus 21 times negative 1, that makes plus 21. That looks more like it, although, you know what I think we have? We have our imaginary part first. This is like bi, and then the real part. But you want it to be switched. So I'm going to switch the two. I'm going to put the real part first, 21, and then the 6i second. Now it looks like a plus bi. Even though it's a minus in the middle, it doesn't really matter. It could be a plus bi or a minus bi. So far I think it looks good. Alright, so it was a little more work, right? But the good thing is you kind of do what you would think to do. You're distributing the 3i in as if it were kind of polynomials and you're dealing with those. So it's not too bad, it's just, you really have to remember that I squared is negative 1. So from here on out in this section, anytime we see an I squared, immediately I'm going to think, ooh, replace it with negative 1. Every single time. Alright, and then over here in part B, what do we have? Looks like a little more complicated, but you know what it reminds me of? What if you replace the i's with x? If it was negative 4 plus x, and then 5 minus 3x. I would think FOIL, right? Because it's a binomial times a binomial. And that's exactly what we do. It'll be really similar, it's just we might end up with the I squared again. Once we end up with the I squared, I'll have to replace it with negative 1, but no big deal. Okay, let me see. I'm going to FOIL it out. So we got first times first, that's negative 4 times 5, which is negative 20. Outer times outer, negative 4 times negative 3i, that's a positive 12i. Inner times inner, I times 5, that'll be 5i. The last times the last is the I times the negative 3i, that'll be negative 3i squared. Alright, so I think at this stage, I kind of have two things to do here. The two middle guys are like terms. 12i and 5i, it's like 12x and 5x. We can combine those to get 17i. And then here you have I squared, but like we saw in the last problem, whenever you see an I squared, you're going to want to replace that guy with negative 1. Everywhere. Because I squared is kind of useless. Because remember, you want to see your answer in the form a plus bi, and there's no I squared in there, so you want to make sure anytime you see an I squared, get rid of it. And now we'll see what happens. What do we have? I'm just going to rewrite the first two terms. They're exactly the same, because there's not much I can do with them. But then here we have Negative 3 times negative 1, that's positive 3. And now that we've replaced I squared with negative 1, I notice that we have some like terms here. Negative 20 and 3 combine to make negative 17. And then plus the other guy, 17i. There we go. That looks like it's in the right form. You got your real part first, a, plus, here's bi. Perfect. There it is. So it's a little more work. It's just, once you FOIL, you got to kind of clean it up and stuff like that. All right, one more of these, and then we'll move on to division. So here we're dealing with kind of the same type of thing. I might want to FOIL. But you notice these kind of look like conjugates, like we talked about a few sections back. Because you notice these are the same terms. You have a 4 and a 4, so same terms. 3i and 3i, but the signs in the middle are opposite, right? A minus and a plus, or if it was a plus and then a minus, same thing. So remember before, kind of magical things happened when we multiplied conjugates. Let's see if the same thing happens here. Let's see, we're going to FOIL it out. First times first, that's 4 times 4, which is 16. Outer times outer is 4 times 3i, that's 12i. The inner times the inner is a negative 3i times 4, that's a negative 12i. The last times the last, negative 3i times positive 3i is negative 9i squared. Alright, so it's kind of similar to the last one. I have like terms in the middle, but this time the like terms in the middle cancel. 12i minus 12i is 0, which kind of should ring a bell as far as conjugates go. Remember when you multiply conjugates, your outer and your inner are going to cancel. And as far as that last term goes, you have a negative 9i squared. But remember, every time you see an I squared, you want to replace it with negative 1. Without even thinking about it. It should become second nature. So you have 16, it's negative 9 times negative 1 is positive 9. If you add those together, you get 25. Wow. So that's it. Even though that doesn't look like a complex number, it could be 25 plus 0i, if you wanted to really make it look like a plus bi. That's interesting, though. It's probably worth pointing out, and I think that'll be helpful soon, that when you multiply conjugate complex numbers like we have in this problem, then you get what? You get a real number. Notice there was no imaginary part when we ended. But the previous two parts that we did in this example, we ended with an imaginary and a real part, and the previous one as well. This was the first one we've seen where the imaginary part disappeared. It was just it's all completely real. I think that'll be helpful in the next problem, knowing that two conjugates multiply to make a real number. Alright, let's see. What are we talking about here? We've learned how to add and subtract complex numbers, but not divide, or multiply, but not divide. So here they give us directions. We say, to divide complex numbers, you multiply the numerator and denominator by the conjugate of the denominator. So it seems kind of weird because the directions are divide, but you're not really dividing. Like it says, you're multiplying. So it's kind of weird. It's a lot like, what's it called? Remember when we rationalize the denominator? Like rationalizing the denominator. Yeah, a few sections back, we said, oh, if there are two terms in the denominator and you want to rationalize it, you have to multiply top and bottom by the conjugate of the denominator, if you remember. So it's really similar to that. So you know what I usually say is, in these problems where they say, oh, divide these complex numbers, I usually add, just for fun, quotations around the word divide, because you're not doing any division, you're doing multiplication. It's weird. So I guess in part A, you're thinking of 26, the numerator, as one complex number. You're trying to divide that by the denominator, 5 plus I. So I guess if you want to rewrite it, just to kind of think about it, it's like 26 divided by 5 plus I. And, you know, looking at that, it's like, how am I going to divide those? 26 divided by... There's not really a way to divide these, especially keeping in mind you want your answer to look like A plus BI. How the heck am I going to do that? So it's kind of next to impossible to figure this out unless you just follow what they say. You're not really dividing, you're multiplying by the conjugate of the denominator. So remember, conjugate of the denominator, that's where I have the same term, so I have a 5 and an I, like the denominator has, but there was a plus, I want a minus, because conjugate has the opposite signs. That's really the trick, and it's not easy to remember that. That's kind of a seemingly random thing to do. So really the trick for these problems is trying to memorize, when they say divide, they don't really mean divide, they mean multiply by the conjugate. So I'm going to rewrite it just to be careful. In the numerator, I'm multiplying 26 by 5 minus I. The denominator, I have 5 plus I times 5 minus I. So I'll just distribute in the numerator. 26 times 5 is 130. And then I have 26 times negative I, that's negative 26I. So the numerator looks good. How about the denominator? I have to FOIL that out. First times first, 5 times 5 is 25. Outer times outer, 5 times negative I is negative 5I. The inner times the inner is a I times a 5, that's another 5I, but positive. The last times the last, an I times a negative I is a negative I squared. Here we are. And in the numerator, there's not much you can do because you have a 130 and a negative 26I. Those are not like terms. So there's not a whole lot you can do there. They'll just kind of be waiting to see what happens in the denominator. And this is a point where I should have remembered the outer and the inner cancel. Of course, when you multiply conjugates, remember, outer and inner terms will cancel. So if you want, you can just multiply the first and the last and forget about the outer and the inner, because they'll always cancel every single time. So what's left over? The 25, that was the first term, and then minus I squared. But remember, we said anytime you see an I squared, you want to replace it with negative 1. So I'm going to replace that guy. Just don't forget he had a negative in the front, so I have to keep the negative, or subtraction, and then I squared itself is negative 1. So now the denominator just becomes a real number. Whoops. The numerator's just kind of sitting there waiting. It's 130 minus 26I over, let's see, that's 25 minus negative 1, which is 25 plus 1, or 26. Okay, and this is where I might want to try to reduce or something, but I can't reduce, remember, unless you factor. I can't cancel the 26 and the 26, because you can only cancel in a rational expression like this if the thing you're trying to cancel is a factor, like you factored it out of the numerator and denominator. So probably what I would do is split this up into two fractions, just to make it safe. Into two fractions, and I'd like to do that for two reasons. One, because then you won't be tempted to reduce things you're not supposed to reduce, like those 26s. I'm not ready to reduce those yet, and we'll see why. But also because, remember, you want your answer in the end to look like A plus BI. And right now it does not look like that. It looks like one big fraction. When you want A and BI, the real and the imaginary parts, to be separate, not part of the same fraction. This will kind of kill two birds with one stone. And we can do that because, if you remember, when you have only one term in the denominator like we have, you can kind of give each term in the numerator its own special denominator. So the 130 can get its own denominator of 26. The 26I can get its own denominator of 26, and then we can reduce from there. Okay, and you know what? It actually turns out that 130 over 26 goes into 135 times exactly. Isn't that crazy? So this guy reduces to 5. And of course here, 26 over 26 is 1, so you're just left with I there. And now it does look like it's in the form A plus BI. I have my real part on the left, the imaginary part on the right, and there it is. That must be the solution to this division problem. Crazy. But notice if we go back and we try to reduce at this stage here, remember we said, well, it's really tempting to cancel these 26s. Well, then if you cancel the 26s, you'd still have a 130 left, and the I. But notice that's not what it's supposed to be. It's supposed to be a 5 minus I. So you really had to involve the 130 in the reducing as well, not just the two 26s. And that's why I always do, like I said here, is split it into two fractions before I try to reduce or anything. That way I'm not tempted to reduce things I'm not supposed to. And that also kills the other bird of, you need to write this as A plus BI. So this can't be one big fraction. It has to be two separate terms. Ugh, so division, for sure, you can tell it's a lot more complicated than multiplication. But it's really just tedious. I mean, the first thing is you have to memorize that you're multiplying by the conjugate. That's kind of hard to remember. But then also, it's just really tedious, even if you remember that. Ugh. But for part B, we have 3i over 4 plus 2i. So like it says in the directions, I want to think about what's the conjugate of the denominator. And like we said, the conjugate has the same terms, 4 and 2i, but opposite sign. Now, since I see a plus, I want a minus, the opposite one. And then from there, I'm going to go ahead and be really careful. In the numerator, I've got a 3i, and I'm multiplying that by the 4 minus 2i. In the denominator, it's 4 plus 2i times 4 minus 2i. All right, in the numerator, let me distribute that 3i there. 3i times 4 is 12i. 3i times negative 2i is negative 6i squared. In the denominator, this time I'm going to be really clever. Because I remember I'm multiplying conjugates. The outer and the inner are going to cancel. I'm just going to do first times first. 4 times 4, that's 16. And then last times last, 2i times negative 2i is negative 4i squared. Because the outer, if I do 4 times negative 2i, the outer, and then the inner, 2i times 4, that's a negative 8i and an 8i, and they're going to cancel anyway, so why even bother? And this is a stage where it's kind of a little bit tempting to reduce as well. Maybe these I squared, you know, but remember you cannot reduce unless you factor something out. So I can't reduce yet. What you want to do is try to simplify the numerator and denominator as much as you can separately, and then think about reducing. So in the numerator and denominator, notice that there's an I squared. The first thing I'm going to do is replace both of those I squareds with negative 1. So, okay, here was an I squared. He's going to be replaced with negative 1. Here was an I squared. He's going to be replaced with negative 1. And then we'll see what happens from there. In the numerator now it's 12i minus 6 times negative 1 is plus 6. In the denominator we have 16 minus 4 times negative 1 is positive 4. So we're getting there. This is looking closer to the last problem. So we have 12i plus 6 over 16 plus 4 is 20. There we go. And this is a stage where I want to reduce really bad, but I got to remember this rule here. Don't try to reduce until you split it into two fractions. So it's going to end up being the 12i over the 20, that's going to be the first fraction, and then the 6 over the 20, that's the second fraction. So okay, like we said, 12i over 20, that's the first fraction it splits up into, plus 6 over 20. And I'll try to reduce either of those. So 12 over 20, that reduces by 4. 4 can go into 12 3 times, and 4 can go into 25 times. The second fraction, though, it can only reduce by 2. 2 goes into 6 3 times, 2 goes into 20 10 times. But make sure you split it before you reduce, because that wouldn't work very well if I tried to reduce it before splitting. And then, like in all these problems, you want to make sure, am I ending with this type of answer, a plus bi? I think pretty much, except the I is on the left here, but I want it on the right. So my last step would probably be switch the two terms. I'll put the 3 over 10 first, because that's kind of like my real part, the a. And then 3i over 5. You know what also you can do is write 3/5 and then the I on the side. Just because, you know, you usually see it as I times something. This doesn't look like I times something. It looks like I within a fraction. So that's something you're free to do as long as you can always take an I that's in the numerator and throw it off to the side. No problem. There we go. That looks a lot more like A, which is 3/10 plus bi, and b is 3/5. Yeah, okay. Sounds good. That was complicated, right? Ugh. Alright, let's try a couple more of these, and then we'll move on to the very last topic in this section, which is actually a lot easier than... This is probably the toughest part right here, so if you can do this, bear with me, then you'll be fine. So part C, this one's more complicated because this is the first of this example where we've seen two terms in the numerator. So far it's only been one term in the numerator, but it doesn't matter, we'll do the same concept. We have the denominator 5 minus 3i, I want his conjugate, that's 5 plus 3i. Numerator and denominator. You can tell that I'm going to have to FOIL on the top and FOIL on the bottom because I have two terms times two terms in both cases. Okay, numerator, let me FOIL it out. First times first, 6 times 5 is 30. Outer times outer, 6 times 3i is 18i. Inner times inner, 2i times 5 is 10i. Last times last, 2i times 3i is 6i squared. So that's the numerator. I'll work on that later. The denominator now I have, remember these are conjugates, 5 minus 3i, 5 plus 3i. So all I really need to do is multiply the first and the first and the last and the last. No need for outer and inner. First times first is 25. Last times last is 3i times negative 3i, that's negative 9i squared. Alright, looks good. In the numerator I have a couple like terms in the middle. I'll combine those guys. It's 30 plus, we have 18i and 10i mixed, 28i. And then the next term we have 6i squared, but of course whenever we see an I squared you want to replace it with negative 1. That's all I can do for now in the numerator. In the denominator, that's really all I can do as well. Replace that I squared that's multiplied by the 9 by negative 1. There we go. Alright, and we'll simplify and we'll be close to being done, I think. These get easier the more of them you do. They're still tedious no matter what, but they still get a little easier. Let's see, we have 6 times negative 1, that's negative 6 in the numerator. And the denominator we have 25 plus 9 now, since it's negative 9 times negative 1. Okay. In the numerator there are a couple like terms. 30 and negative 6 make 24. Plus the 28i, that was already there. In the denominator now we have two like terms. 25 and 9 makes 34? Yeah, I think that's right. And before I try to reduce, I notice that all three of these numbers are even. But if I only reduce two of them at a time, that won't be right. I have to kind of involve everyone in the reducing. So I'm going to do like we did before, and split up the fraction. We're at 25 over 34, and then the 28 over 34. There we go. And 34, it's only 2 times 17, right? So I don't think I can reduce much. It's only by 2. 2 can go into 24 12 times. Goes into 34 17 times. 2 goes into 28 14 times, and it goes into 34 17 times. There we go. And of course, I'll throw the I off to the side. And that does look like it's in the right form. It's something real plus something real times I. All right, looking good. All right, I think probably by now you get the hang of it. And it's painful. I mean, it's just tedious, not really painful, but yeah, by now you probably get the hang of it. And this last one will just be kind of to really cement it in. So here again, we want to think about what's the conjugate of the denominator, 3 minus 6i. Just, yeah, whatever the opposite sign is. Same terms, opposite sign. All right, now we got to get really serious. We want to FOIL out the top. 5 minus 2i times 3 minus 6i. And then FOIL out the bottom. 3 plus 6i, 3 minus 6i. Although we know you don't have to multiply the outer and the inner for the denominator. But for the numerator, you do. I've got numerator first times first is 15. Outer times outer, negative 30i. Inner times inner, negative 6i. Last times last, positive 12i squared. In the denominator, we have just the first times the first, 9. Last times last, negative 36i squared. Don't even bother with the outer and the inner. They're not worthwhile because they're conjugates. So they're going to cancel. So just like we've seen before, we have a couple like terms on the top that can be combined, and these I squareds that are in the numerator and denominator. I'm going to replace them both with negative 1. I'm going to get ready right now. So the numerator we had 15, and then the like terms are negative 30 and negative 6. That's negative 36i. And then we had plus 12 times negative 1 because it was replaced for I squared. In the denominator, we had 9 minus 36i squared, but I'm replacing the I squared with negative 1. And now it's a matter of simplifying the I squared, or the negative 1 parts. 15 minus 36i, and then we have minus 12 over, that becomes 9 plus 36. In the numerator, we have some like terms. 15 and negative 12 makes 3. Oops, minus 36, sorry. The sign in front of 36 doesn't change, of course. 36. 9 plus 36 is 45, I believe. Alright, and I think I could see some reducing happening here, but I better split it into two fractions. 3 over 45, and then minus 36 over 45i. And once we reduce, that's all we can really do. So let's see, 3 goes into 45 15 times. So that first fraction becomes 1 over 15. But notice that I think 9 is the largest thing that goes into both of these. 9 goes into 36 4 times. 9 goes into 45 5 times. So that guy really becomes a 4/5. It reduces quite a bit. All right. Last topic in this section, or actually in this chapter, huh? This is the end of this chapter. Sorry if you're a little bit sad about that. It's a bummer. No, just kidding. No, but the last part of this section is kind of talking about higher powers of I. And I don't mean something in a religious sense. I mean, like these guys down here. This example, I to the 26th power, I to the 100th power, I to the 57th power, etc. So these guys, it sounds like, oh my gosh, how am I going to figure that out? That means I times itself 26 times. That's a pain. But actually, it turns out that powers of I are pretty simple, or they kind of repeat themselves in a way. So we'll see here. The ones we already knew, well, first of all, if you raise anything to the 0 power, you get 1, right? Even though I is an imaginary number, it's still true. Anything to the 0 power is 1. So we got that. Oh, and then notice there's a little mistake here. This should be a 1, sorry. I to the 1 power, because we're trying to increase the powers every time, is I. And then I, we know, we defined it to be the square root of -1. So we already knew that one. And then also the first one, anything to the 0 power is 1. We got that. These ones aren't new. And we've been using this fact here, I squared is -1. But what about the next guy, I cubed? So that one, if you wanted to, just for fun, if you kind of care, maybe off down here to the bottom, you could kind of think about what I cubed is. I know what I squared is and what I to the 1 power is, but I cubed I don't know. But if you think about it, I cubed, that's I times I squared, if you want to split it, right? Because if it's I to the 1 times I squared, you'd add the powers and get 3. And I split it that way because I know what both of these are. I to the 1 power, we defined it to be the square root of -1 times I to the 2nd power is -1. So it's like a -1 times a negative root is negative root -1, kind of. So that's where they get this idea here. And if you think about this guy, this is I, but with a negative in the front. So it's really -I. That's where they get that. And then the next highest power of I up here, I to the 4th, that one you can kind of split in an easier way. I to the 4th, it's I squared times I squared, because you would add the powers and get 4. And both I squared and I squared are -1. And -1 times -1 is +1. And that's why we see up here that I to the 4th is +1, sorry. And if you keep kind of going in this fashion, if I look at I to the 5th, and I split it up, maybe, maybe write it down just for fun. I to the 5th, if you split it up into, I don't know, I to the 3rd times I squared or something, or I to the 4th times I, you can split it up as long as it adds up to 5, and then replace them with what you know. I know that I cubed is -I, because we already saw that up here, and then I squared is -1. So if you have -I times -1, that's +I. That's where they get the next one. I to the 5th is I. And and you can kind of imagine you keep going that way. If you wanted to figure out what I to the 6th was, you'd split it up into, I don't know, I squared times I to the 4th, or I to the 3rd times I to the 3rd. Doesn't really matter, you just keep splitting it. And if you keep doing that, you keep going, I to the 6th, I to the 7th, I to the 8th, 9th, 10, 11, 12, 13, etc., etc. You see that the values it takes on, notice, they keep going like the same values. It was 1, I, -1, -I. And when you started I to the 4th, same ones. 1, I, -1, -I. And if you start at I to the 8th, 1, I, -1, -I. And on and on and on. So really, any power of I will be one of these numbers. That's good to know. Yeah, any power of I. It doesn't matter how high of a power. If you go up to I to the 1,000,000th power, it'll be one of those 4 things. It'll be 1 or I or -1 or -I. One of those 4. So really our job when they tell us to simplify I to some power is just determine which one of those it's going to be. And it's kind of, you can tell that it goes through a cycle of 4 values. I to the 0 is 1. I to the 1 is I, etc., etc. So all we have to do is figure out where in this cycle does it land. We have a way to figure it out over here. Where is it? Here we go. To simplify a power of I, you divide the exponent by 4, and that's because that's the length of the cycle. There are 4 different values it could take on. The remainder is an equivalent power on I. Oops, I spelled is wrong. Isn't that sad? Should be is with an I, not os. Is that even a word, os? Probably not. Alright, so like it says, you divide the power that you're given by 4. And it's not like the quotient, the answer you get, is equivalent power on I. Like it says, it's the remainder that's an equivalent power on I. So it's kind of interesting. Let's try it, and then maybe we'll talk about why that is a little bit. Let me see, I'm going to erase all this junk down here. This is just kind of giving you an idea of where they get those values. And you could keep going with that, trying to figure out I to the 5th, I to the 6th, on and on and on. But I think someone was doing that, and they figured out, you know what, this is a cycle of 4 values. I just got to figure out which of the 4 will it land on when I'm looking for my specific power. Oops. All right, let's try this. I to the 26th here. We got, like the directions say, you're just dividing the power by 4. And if you're wondering, 4 always? Yes, 4 always, because there's only 4 values that I to a power can take on. So no matter what power you're looking at, you're always dividing it by 4. It doesn't matter what it is. So let's see, 4 can go into 26 at most 6 times, because 6 times 4 is 24, and the remainder is 2. So like the directions say, it says, it's not like you want the 6, which is the quotient, you want the remainder. This means that the problem we were given, I to the 26, it's the same as I to this power, 2. And that's something we know. That was one of the very first things we learned. I squared is -1. So there you go. That's your answer. I to the 26th power is -1. And so I guess if you're wondering, like, why is it the remainder that's the answer, you know? Why isn't it the quotient? So the quotient, I guess, again, remember that these values are cyclical. It's a cycle of 4. So it's, if you're looking at it here, I to the 0, I to the 1, I to the 2nd, I to the 3rd. You start over again. I to the 4th, 5th, 6th, 7th, 8, 9, 10, 11, 12, 13. So if you look at the quotient here, 6, that tells you how many times you would have gone through this cycle before you got to I to the 26th. We don't really care how many times we went through the cycle. We care about where we land, and the remainder tells you where you land. It's saying, okay, you go through the 6 times. 1, 2, 3, 4, that's once. 3, 4, 5, 6. Okay, that's you went through the cycle twice. And the 6 is saying you went through that cycle 6 times before you landed on I to the 26th. But I don't care how many times I went through it. I want to know where I landed. And that's really what the remainder tells you. Where did you land in the cycle, the second one down, you know? So anyway, that's kind of why. If you care, a lot of people don't care anyway. I don't know why I'm saying it. All right, let's try the next one. Same kind of thing. You're always dividing the power by 4 no matter what. This time the power is 100. And 4 happens to go into 100 25 times evenly, right? So the remainder is 0. That means the problem we were given, I to the 100th, is the same as I to the 0 power. And like it pointed out above, anything to the 0 power is 1, so our answer is 1. That means I to the 100th power is 1. So it's weird. There's a lot of things in this section that if you care enough, they make some sense, but if you don't really care, you're just doing a lot of memorizing without really understanding. This is kind of one of those things. If you don't really care, just remember you're dividing the power by 4, and you're grabbing the remainder and throwing it on I, and that's it. So we can do that here. 4 into 57. Remember, it's always 4 you're dividing by. 4 goes into 5 once. Goes into 17 4 times. And the remainder is 1. Okay, so that's what I want. That means I to the 57th power is the same as I to the 1 power. Or I, you know. Or if you wanted to say it's the square root of -1, that's fine, because that's the definition of I. Man, it's weird stuff, right? Very weird. One more, and I think we'll get the hang of it. Just again, you're just dividing the power by 4 every time. See, 4 can go into 8 twice. It goes into 3 0 times. So the remainder is 3. That means I to the 83rd is the same as I to the 3rd. And I to the 3rd, if you go back, it's -I. That's the thing we're looking for there. All right, and that's it. So on these problems, when they say simplify powers of I, your answer is always going to be one of these values over here. It's 1I, -1, or -I. Always one of those 4 guys right there. Because your remainder, when you divide by 4, your remainder will always be 2, like this was, 0, like this was, 1 like this was, and 3 like this was. It'll always be 0, 1, 2, or 3. So all right, hopefully that made some sense. This was a tough section, but at least it's the end of the chapter, right? And then we'll start the next chapter, and it'll be a lot better. So thanks for paying attention. I'll see you in the next video.